Okay, so this is our system now, a one-dimensional chain, sites labeled 1, 2, 3, etc. Site I and site J and so on. We have a certain number of these sites. And I drew also one particle here and two particles here to illustrate the Hamiltonian that we will be discussing. So now we need to define the quantum operators that will allow us to write the Hamiltonian. So AI is a quantum operator that destroys the particle on site I. Its conjugate, a dagger, let's take it on site J, is an operator that will create a particle on site J. The commutator, which is of course AI, AJ dagger minus AJ dagger AI, this is equal to delta IJ. It is 0 if I and J are not equal, and if they are equal, it is equal to 1. Okay? The number operator, this is an operator that counts how many particles are on a particular site, is given by AI dagger AI. So AI destroys a particle on site I, and the dagger creates the particle. So if I want to describe this particle jumping from here to here, this is site I plus 1, that term would be I need to destroy a particle on site I, AI plus 1 dagger. And since everything in a Hamiltonian, the Hamiltonian must be Hermitian, I need to add the Hermitian conjugate, allowing the Hamiltonian to destroy a particle on site I plus 1 and creating a particle on site I. So the particle can jump like this, but it can also do the reverse. So this will be the kinetic energy term. Okay, this is the term that describes how the particles jump from one side to another side. Now, what happens when two particles meet? As I mentioned before, there is an energy cost to that. What is that cost? Let us say it is U over 2 times Ni minus 1. Remember, Ni is the operator that counts the number of particles on site I. So, if Ni is equal to 0, the energy cost is 0, because I have 0 multiplying everything else. If Ni equals 1, I only have one particle on the site. There is no cost in energy. 1 minus 1 is 0. So the cost is 0. If I have two particles on the site, 2 times 1 is 2. So then the cost is just U, and so on and so forth. So this term gives us the energy cost when particles meet. It has to be more than one particle. 2, 3, 4 particles, there's an energy cost. This now allows us to write the full Hamiltonian describing the system. H is equal to minus T, the sum over I, AI dagger AI plus 1, plus the Hermitian conjugate, as we discussed down here, plus U over 2, the sum over I, Ni minus 1. Now the sum over I must go over all the lattice sites of the system, so it goes from 1 to L. We assume we have L such sites, from 1 to L. But notice here I have I plus 1, so when I is equal to L, L plus 1 simply means we come back to the first site. This is called periodic boundary conditions. Imagine this chain is in fact on a circle. The circle has no beginning and no end. You start at site 1, you come back to site L, and then you continue again. Now, this term here, just to fix ideas, this is the kinetic energy, as we said over here, and this term here is the potential energy. So now we want to do calculations. To do calculations, we need, since we have the Hamiltonian, now we need the quantum state. We need to describe the quantum state. So let us define this notation. This is the quantum state, and it is given by N1, N2, N3, Ni, Nj, etc., all the way up to Nf. And what I mean by this notation is that on site 1, I have N1 particles. In this drawing here, there are no particles on site 1, so N1 would be 0. And 2 is the number of particles on site 2. In this case, I drew only one particle, so N2 is equal to 1, N3 is equal to 0, and I is 2, and J is 3, and so on. So this is the representation I will be using. It's called the occupation number representation of the quantum state. So if I apply a number operator, for example, if I apply a J dagger, a J on this state, this operator will count the number of particles on site J. So I will get Nj times same state back. Okay? And if I apply a destruction operator, let us say, for example, I apply AI on this state, AI will act only on this site. So that will give me Ni over the square root, it is a normalization, times the state, N1, N2, Ni minus 1, because I destroyed a particle on site I, Nj, etc. Nothing else changes, but only one particle is destroyed here. If I apply a J dagger, let's say, on the state, I'm going to get N1, N2, Ni is not touched now, Nj is now Nj plus 1 because I created a particle on site J, etc. And again, there's a normalization here, Nj plus 1. So this is the representation that we will be using. And so now, to create a state, what do we need? We need the empty state, the vacuum, which we denote by 0, and which has the property that any destruction operator acting on the vacuum, that just gives us 0, and then we can build our states from this empty state. So the state with n particles on site I, let me write it like this, a state which has n particles on site I can be created by applying the creation operator Ni times. So on site I, the creation operator is AI dagger. I need to apply it Ni times. It acts on the vacuum. Every time it acts, it creates a particle. But you should not forget our normalization. Remember these normalization factors here. So here, this would be divided by the square root of Ni plus 1 factorial, because every time we create a particle, there is such a normalization term, so it multiplies, it accumulates, and so we get the factorial. So this is the representation which we will use to describe what these particles are doing when the Hamiltonian is acting on this state. And we end this discussion by adding two properties of the states that we will need later, so that these states are normalized, as I mentioned, that if I take the inner product of this state with itself, we have 1, and the inner product between two states that are different in any way, this is 0. And different in any way, it could mean that they have the same number of particles everywhere except at one site they're different, then immediately we will get zero. So we will need these properties in the calculation which will follow. So now we have the Hamiltonian. We would like to study it to try and map out the phase diagram of this system. I have a number of particles in the system jumping from site to site and interacting with each other. This Hamiltonian is too complicated to analyze as it is. We need to make some sort of approximation. Let us make the simple approximation where the hopping parameter t divided by the interaction u is very, very small. This means that I can ignore this term, the kinetic energy term, compared to this term. If we do that, you see that the sides of the lattice are no longer connected because the only connection between them comes here. So now we have a Hamiltonian which describes a collection of independent sides. So we can write it like this. Which I will write now as sum over I from 1 to L epsilon I of n I. So we can calculate the energy of on every site as a function of the number of particles on that site. Let's do some of those. So epsilon I of ni equals 0. That's clearly 0. Epsilon I ni equals 1. That's also 0 because I have 1 minus 1. Epsilon I of ni equals 2. That's just u. I'll do 2 more. Epsilon I of ni equals 3. That is 3 times 2 is 6, divided by 2 is 3u. And the last one is epsilon I ni equals 4. That's equal to 6u. And so on. So since we can have several particles on every site, I would like to study how the system behaves as the number of particles changes. Now, one way to change the number of particles is by changing the chemical potential. This is in the grand canonical ensemble. So how do we define the chemical potential? The chemical potential is the energy cost to adding one more particle to the system or removing one more particle. It is the free energy cost. So the chemical potential at n particles is equal to the free energy at n particles after we added the particle minus the free energy at n minus 1 particles. Now the free energy, I remind you, is equal to the energy minus temperature times entropy. But since the system is at 0 temperature, this term goes away and the free energy is just equal to the energy. So then I can just write here epsilon of n minus epsilon of n minus 1. So we have a way to calculate the chemical potential. Now, note that here we have a thermodynamically stable system. The chemical potential must be the same everywhere in the system. It cannot be dependent on position. And that's why I no longer have I here or I here, because whatever the chemical potential is on a given site, it must be the same on all sites. So now let's calculate the chemical potential for a number of cases. We have all of these energies. Let us calculate then the chemical potential for having one particle. Well, it is this energy minus this energy. As you see, it is equal to 0. Let's calculate the chemical potential for having two particles. Now that's equal to this energy minus this energy. That's equal to U. The chemical potential for having three particles, it is this minus that. That's 2U. And the last one I will do is the chemical potential for having four particles is equal to this energy minus this, and that is equal to 3U. So you see here that there are intervals of chemical potential for which the density remains the same. The number of particles per site remains the same. So for example, if I divide by U, so mu over U, I can divide both sides of each of these equations by u. If mu over u is between 0 and 1, 0 and 1, I have 1 particle per site. If mu over u is between 1 and 2, we have 2 particles per site, and so on. I will write n minus 1 and n. We have n particles per site. So we have now the beginnings of our phase diagram. Let me draw the vertical axis as mu over u. I need the horizontal axis. Now, what will the horizontal axis be? Now, remember, we took t over u to be 0 here. And we calculated all of these things. Eventually, we want to take t over u finite. So we want to go in the finite t over u direction. So let's take this axis to be t over u. And according to what we have found so far, this is 1, 2, 3, etc. Here, in this interval, n equals 1. In this interval, n equals 2. In this interval, n equals 3. So you see, we have a finite interval of chemical potential where the density remains constant. The density remains constant. That means if I take dn by d mu here or here or here, it's equal to 0. But you remember from thermodynamics or statistical physics that 1 over n times dn by d mu is just the compressibility. So what we have found then is that we have these regions where the compressibility is 0. So this is an incompressible phase, and so on. This phase is incompressible, but it's also an insulator because T over U equals 0 implies no transport. The particles are not moving from site to site because the hopping parameter is 0. If there's no transport, it is an insulator. And at the same time, it is incompressible. This is what we call the Mott insulator. It is a phase that exists at 0 temperature when particles repel each other very strongly, as we see here, T over U is 0. So this is the first quantum phase that we have discovered in this model now. We have a Mott insulator. Now the question is, what happens when T over U is finite? If I start here with a Mott insulator, and I start moving into finite T over U, what will happen? Will it disappear immediately? Or will it extend and protrude into this phase? That's the question which we would like to answer next. And for that, we will use perturbation calculation, and we'll only use first order perturbation, which is enough to show us what we are looking for.